This is lesson 3 of chapter 5, and in this lesson we'll talk about periodic trends. Now by trends we mean patterns on the periodic table. The way the periodic table has been arranged is to show many of the properties and patterns of the elements. So there's a really good reason to the arrangement of the periodic table, and we'll find that in this lesson. So the first thing we'll do is talk about ionic character. Remember that ionic means that, or an ion means that a substance has lost or gained electrons. So electrons have been lost or gained. Now, if you are a metal, then the metal will form a positive ion. A positive ion is called a cation. Not cation, cation. And the way you form a cation is by losing electrons. So this is done by losing electrons. This is because electrons are negative, and if you remove a negative from an atom, the positive nucleus is brought out. The nonmetals form negative ions, or anions, not anions, anions, and this is done by gaining electrons. Gaining electrons. So remember, the metals are on the left side of the periodic table, the nonmetals are on the right side of the periodic table. And so on the left side you form positive ions, on the right side you form negative ions. If you are hydrogen, hydrogen, remember, has properties, you can say, of both metals and nonmetals. It has chemical properties of metals and physical properties of nonmetals. Hydrogen usually forms a +1 ion, although hydrogen can form a -1 ion. Can form -1, but usually it does not. Usually the +1 is the most common ion that hydrogen forms. Now a closer look at how and why elements form ions. Consider, here it says elements will lose or gain electrons to achieve a noble gas configuration. So if you take a look at the element sodium, and if you find sodium's Bohr model, you'll see that sodium has one extra electron in the third shell. And if you find chlorine, you'll see that chlorine has or needs an extra electron in the third shell. It has one electron, say, missing in its third shell. So what will happen is the elements will provide each other's needs of electrons. Sodium will actually give up an electron to chlorine, which will accept that electron, so that both sodium and chlorine have a full outer shell. In fact, both of these, if you take a look, there are 8 electrons in the outer shell of sodium. There are also 8 electrons in the outer shell of chlorine. And this is like the noble gases. Remember, every element wants to be like the noble gas. So this is what drives these elements. And we're going to see this on the periodic table a little more clearly. So if you take a look at the this question says, what would a lithium ion look like? What an oxygen ion will look like? What would an aluminum ion look like? In order to see this, let's take a look at the periodic table. So we're first looking at a lithium ion. Lithium is this element here. Now the key to this will be looking at the closest noble gas to these elements. The closest noble gas to lithium is actually helium. So lithium will want to be like helium. Now, in order for lithium to become like helium, it will have to lose an electron. Lithium has 3 electrons, and so it will lose one to become like helium, which has 2 electrons. Now, when lithium loses an electron, it becomes positive. So lithium, when it loses an electron, gets a +1 charge, and this is what lithium would look like. If you take a look at oxygen, here's oxygen. It has 8 electrons. The closest noble gas to oxygen is actually neon with 10 electrons. So oxygen wants to be like neon. It will gain 2 electrons. It will gain this and this electron. And oxygen, when you gain electrons, you become negative. So oxygen acquires a -2 charge. This is the ion of oxygen. And finally, taking a look at aluminum. Aluminum has 13 electrons. Its closest noble gas, now there are 2 possibilities. It could be neon with 10, or it could be argon with 18. So aluminum can go either way. but the closest one is neon. So neon, again, for aluminum, which has 10 electrons. Neon here has 10 electrons. So aluminum would lose 3 to go from 13 down to 10. As aluminum loses 3 electrons, it acquires a +3 charge. And that is how the noble gases predict or help predict what the ions would look like of these elements. This is a very important concept to understand. And as these elements lose or gain electrons, they become stable. So this is how they form compounds. This is a reactivity feature of these elements. Go ahead and try this on your own. Why don't you try calcium, chlorine, and nitrogen with the same concept. Next, we'll talk about the trend of valence electrons. We've defined valence electrons before, and we said that these are the electrons that are involved in chemical reactions. These are the outside electrons of the atom, outside electrons. And the outside electrons occur or are situated in the S and P subshells of that last energy level. So if you take a look at magnesium, here magnesium, the electrons are represented by, valence electrons are represented by these dots. So magnesium here has 2 valence electrons. That's because in shell 3 it has just 2 electrons. Phosphorus, on the other hand, has 5. If you take a look, phosphorus in shell 3 has 1, 2, 3, 4, 5 electrons. 2 in the S, 3 in the P. Fluorine then has 7. Same story. Fluorine has 1, 2, 3, 4, 5, 6, 7 in its highest shell, which is shell 2. 2 in the S, 5 in the P. And by the way, these right here, what you're looking at, are called Lewis dot structures. We will get to them in the next chapter. We'll actually use Lewis dot structures pretty extensively. And it's a quick way of showing how many valence electrons an element has. So why not we do a quick example? This shouldn't be too bad. How many valence electrons in calcium? Here is calcium. Let's go ahead and do a fine color like green. Calcium has 1, 2 electrons in the S subshell, so calcium has 2. Here's oxygen. Oxygen has 1, 2, 3, 4, 5, 6. Easy enough. Iodine. Now, for iodine, it may be a bit tricky, but you're going to ignore the D block. These are not going to be counted. It's just going to be the S, so 1, 2, and the P, 3, 4, 5, 6, 7. So iodine has 7. And iron is also a bit tricky. If you take a look at iron, you again ignore the D block. It's just the S. So it's just 1, 2 for iron. So hopefully this makes sense, especially because we've talked about it. But still, go ahead and try on your own. Try to get me the valence electrons of potassium, chlorine, arsenic, and cobalt. The last trend we'll talk about in this lesson is atomic radius. Now the word radius just means the size, refers to the size of the atom. So by radius we mean the distance from the nucleus to the outside. So this is what we mean by radius. We mean the essentially what you're looking at here is the size of the atom. So you can say size and radius are synonymous in this case. Now the general trend that you can see on the periodic table is, if you were to graph it, is that helium actually is the smallest of all the elements, and down here in the lower left, rubidium in this case, we're actually missing shell 7 is removed, is the biggest. So the smallest in the upper right and the biggest in the lower left, or largest in the lower left. And this is a very important trend to be able to see. And notice how beautiful you can see this on the periodic table. This is proof that we've arranged the periodic table properly. You can see the same thing if you just do a two-dimensional view of it. So here we're just looking at the S and the P blocks. We're actually ignoring, so this is the P block. We're ignoring the D block here, just for comparison's sake. And notice how beautiful this trend looks. Now if you take a look at a group, so if you just take a look at this group here, the alkali metals, you'll see that they get progressively bigger. And this is true of any group. Take a look at the halogen group. They get progressively bigger as you go down. Likewise, if you take a look at a period, say you take a look at potassium, it's period 4, they get progressively bigger going toward the left. And so you can see this trend by group or by period. and here we have it decreasing atomic radius, increasing atomic radius. Again, you see the helium is the smallest, and then in this case we did put cesium is the biggest. So if you take a look, here are the explanations for this trend. This is actually very important to be able to understand the explanations in addition to the trend. So here it says atomic radius gets bigger as you move down a group, and the reason for this is because each time you go down, a new level is started. So if you take a look, every time we go down, we're actually increasing energy levels or shells, and each shell is further away from the nucleus. Remember, if you think of the atom as comprising of shells, each shell is further and further away, and this makes the atom bigger and bigger and bigger. So that's why every time you go down a group, no matter which group, the atoms get bigger, because the shell increases every time you go down. This is the explanation. Now, the other trend of getting smaller as you go across a period, here it says atomic radius gets smaller as you go across a period. The reason for this is because across a period, you're actually still in the same shell. So say if you go across this way, you are still in shell 2. And electrons are filling the same shell, so the nucleus actually brings them closer together. This is because lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, and so on. So you're increasing the strength of the nuclear charge, you can say, just because you have more protons. And because the electrons are still being added to the same shell, to the same area, you're increasing the protons, increasing the protons, increasing, and those electrons are pulled closer and closer and closer. So this is actually a very important trend to understand, not only what it looks like on the periodic table, but also the reasoning for it. So this would complete video 3 of chapter 5.